All right, so there's one last cool thing that we're going to go over here for our thermodynamics. Everybody contain your excitement. All right, so first of all, let's talk about this relationship between delta G, I guess specifically delta G naught, and this other value that we've been looking at to determine whether or not a reaction is going to go towards the products or the reactants, right? What other value have we introduced in this course that we can look at and say, oh yes, this reaction is going to proceed towards the product side? The equilibrium constant. So it turns out that there is a very intimate relationship between the Gibbs free energy and an equilibrium constant. Okay, they are in fact one and the same sort of idea. All right, delta G naught is equal to RT times the natural log of that equilibrium constant. All right, directly dependent on the value of that equilibrium constant. R is a constant that was first introduced in the ideal gas law chapter. It's what's called the ideal gas constant, 8.314 joules per mole Kelvin. Okay, maybe we just want to note that even though that's how our value of R is tabulated, a lot of our equilibrium quantities are done instead in kilojoules, right? So that would be 0.008314 kilojoules per mole Kelvin. And our temperature, if we're talking about delta G naught, what's our temperature? In Kelvin, what specific temperature though? If we're talking about standard state, we're talking about a specific temperature here, 298. Cool. So if we know our equilibrium constant, we can get our delta G, or even more convenient, we can go to our table and get that delta G value and use it to calculate the equilibrium constant for this reaction. So we got to flip this equation here. The inverse would be KEQ equals E to the negative delta G over RT. E is just a special number, kind of like pi. When you take calculus, you'll understand why it's such a special little number. All right, but everybody's got an E button on their calculator. So take a minute to find your E button real quick. Okay, and what we're going to do is we're going to calculate the equilibrium constant for one of these reactions that we studied last class. We reviewed this again at the beginning. But this reaction of nitrogen dioxide going to dinitrogen tetraoxide. All right, last class we used that table and established that the delta G for this reaction was negative 2.8 kilojoules per mole. What is KEQ for this reaction? So KEQ equals E to the now positive 2.8 divided by, and I'm going to put it in parentheses so I don't mess up my order of operations, that R value times my temperature of 298, and I get an equilibrium constant of 3.1. All All right, so based on this equilibrium constant, does this reaction favor the products or the reactants? Products, it's greater than 1, right? So we would say, just by looking at this value, this favors the products. Okay, so that is the same thing as saying that this reaction is spontaneous, has a negative delta G. Anytime delta G is negative, K will be greater than 1. Okay, and does this reaction strongly favor the products? No, it's pretty pitiful actually, right? In this particular case, this very low value of delta G, negative 2.8, is a pretty small number. It's going to give you a relatively small KEQ. If we had a big negative number for delta G, that would imply a large KEQ, right? So these are these two quantities are linked, proportional to one another. Cool, all right. So there's one more thing that we got to learn here about our thermodynamics, okay? Let's think about this. Let's go back to our phase change real quick. We first calculated the delta G of this reaction at 298 Kelvin at room temperature and found that it was non-spontaneous. And that checks out because we're not worried about our water in our water bottle spontaneously boiling here, all right? But let's all remember we also know another phenomenon about water, which is if I did leave a cup of water or a cup with a little bit of water in here over the weekend and it wasn't sealed, I would come back and that cup would be empty, right? Because of a process we call evaporation. Well, this equation right here explains evaporation as well, right? That is just simply water going from the liquid to the gas phase. And that is occurring at room temperature. So how does that check out? How do we say that like, oh, this reaction's non-spontaneous, but we know it occurs right here at room temperature? Granted, very slowly and in small quantities, but nonetheless does occur, right? So how does that check out? This goes back to this idea of standard state. There's one more key aspect of standard state that we have not discussed yet. Right? Not only does it specify the temperature of that reaction, but also the initial conditions, the initial quantities of that reaction. All right, so at standard state, our temperature is 298 Kelvin, but all solutions have a concentration of 1 molar, and all gases have a pressure of 1 atm. All right, so the bottom line is if you have equal quantity of water and gaseous water and steam, then yes, those two will be at equilibrium at that boiling point. But if we have a cup of water in here, the partial pressure of water in the air right now is way, way less than 1, right? So this reaction is not at standard state, which is why it's allowed to occur even here at room temperature. All right, so how do we deal? This is actually really limited, right? Standard state is a limited set of conditions here. The temperature has to be the same, and the pressure of everything or the concentration has to be the same. We don't do many reactions where everything's equal, right? So then how can we use this for any other point other than standard state? Well, we had this quantity that we used to deal with that situation before when we were in our equilibrium chapter, what we called the reaction quotient. And we use this variable Q. All right, your reaction quotient, remember, this is just your equilibrium expression. You build it the exact same way as you build your equilibrium expression. The only difference is the values that you plug in don't have to be equilibrium values, right? Q is what you use for any other set of conditions. So Q is used for conditions outside equilibrium. All right, so let's use this same reaction that we've been discussing. right, and everybody take a second and build me my reaction quotient here. All right, we'll do it in pressure since we got gases. That'll be the most convenient way. Remember, just like our equilibrium constants, products over reactants, so the pressure of my product divided by the pressure of my reactant. I just have to remember, because there's this stoichiometric coefficient of 2 in my balanced chemical equation, that I gotta square that reactant concentration. Okay? So remember, what we calculated for our delta G here was at standard state. Which again was that 298 Kelvin. But also we learned, specifically tells us that the pressure of these gases were 1 atm. All right, that's what that delta G value, that delta G naught value is telling us, is if the pressure of both of these gases were the same, 1 atm, then this reaction would spontaneously proceed towards the product side. I'd make more product under those conditions. All right, but again, what about any conditions outside of our standard state? We're going to use Q for. So first of all, what is Q at standard state? If I plug in that 1 atm for my pressures here, what's 1 divided by 1 squared? 1. So Q is 1 at standard state. Okay, so now let's ask ourselves, is this reaction spontaneous when the partial pressure of my product is 3.5 atm and my reactant is 0.5 atm? All right, so what we calculated before this delta G is for when both of these gases have a pressure of 1 atm. I got an equal amount of both of them. Right? So what I'm going to do now is say, all right, well, I don't care about those conditions. I'm going to increase the pressure of my product, right, and decrease the pressure of my reactant. And I want to know if this reaction is still going to spontaneously proceed towards the products in that forward direction. All right? So we got one more equation to introduce here that we will need to solve this, and that is the relationship between delta G and Q. So the delta G, and notice there's no naught here, meaning we're outside standard state. This is equal to the delta G naught, right? So at standard state, plus RT natural log of Q. R and T are, again, as we discussed, the ideal gas constant and the temperature. We calculated our delta G naught here, right? So in our equation, we got everything we need. We just need to figure out what Q will be under these conditions. So everybody take our equation here and calculate Q for this set of conditions here. right, for this reaction here, our Q will be 14. So now we're going to plug in our negative 2.8. We're in kilojoules per mole here. So when I add R times T, I'm going to use that kilojoule value for R. Times the times the temperature. Times the natural log of 14. Everybody take a second, make sure you can find that natural log button on your calculator, usually located right next door to the regular log button. And we punch that all into our calculator. We get 3.74 kilojoules per mole. So this is now our delta G for these conditions where we're outside of standard state, right? We're no longer at a pressure of 1 atm for both of our gases. We are outside of standard state. Our product was 3.5 and our reactant was 0.5 atm. Okay, so is this reaction going to be spontaneous or non-spontaneous under these conditions? So this would be non-spontaneous. Right? This thing was already pretty freaking close to equilibrium at a pressure of 1 atm for each gas, right? We had a relatively modest delta G, gave us a relatively modest KEQ value. So when we increased our products and decreased our reactants, right, according to Le Chatelier's principle, that should shift things towards our reactant side. And indeed, we shifted it so much towards our reactant side that now our reaction is non-spontaneous. All right? Now, we call it non-spontaneous, but really a better way to be thinking about this, well, what just happened, is that it's spontaneous in the reverse direction, right? Remember, we've updated our way of thinking about chemical reactions from Chem 1A. We don't think about them as just going one way. They're going both ways, right? And they're always going to go towards their equilibrium value, right? Everything's trying to reach equilibrium. So the question is, which way is it going to go to get to equilibrium? A negative delta G means you're going to make more product in order to reach equilibrium. A positive delta G means the reaction is going to happen in reverse in order to reach your equilibrium value. Okay, so by non-spontaneous, what we really just calculated is under these conditions, our reaction is going to go in the reverse direction. All right? And this isn't too crazy because that's exactly what we used Q for last time. When we introduced this concept of our reaction quotient before, it was to compare to our KEQ value and determine whether a reaction is going to go forward or backward. We're basically doing the same thing here, but using this different thermodynamic value, delta G. And again, the nice thing here is this link between delta G and our KEQ. Right? We can get our delta G naught just from these tabulated values here for any reaction that we want, right? And with these equations that we laid out today, we can figure out whether that reaction will occur spontaneously or non-spontaneously at standard state, at any temperature outside of standard state, and under any conditions outside of standard state. All right, so pretty powerful stuff. I know, everybody's like, wow, what a cool week in chemistry. Cool. All right, that's all I got for y'all for today.